gives you an image of the activity of the brain. Sometimes it is not possible to inject something inside, and in that case you can excite the object from the output, from the outside. So you send, for example, a microwave to this object. This wave will interact with the object. The result of the interaction you can measure, and again from this interaction you can make an image of the inside of the object. So this was called passive imaging because the object by himself was giving something. Here is an active imaging, and in the active imaging you may have the possibilities to work in transmission or in echography, in reflection. You send waves, waves goes through the body. Here you make the measurement, this is transmission. Or you send the waves, goes to the object and come back, and you measure reflection. This is, for example, the famous echography to seeing a baby inside the body. And this in place of the microwave, if you send the X-rays, then you have, for example, the CT scanners in this case. So we wanted to see outside. No, we wanted to see inside of a body. So this is the third example that I'm going to show. Exactly, talking about the X-ray, let me show you how works an X-rays. Here you put a source of X-rays. Here is the body. The X-rays goes through the body. At the other side, you put the detectors. These detectors measures the quantity of the intensity of the X-rays coming here, and you make these measurements all around the body. Actually, everything is inside here. You have the sources of the X-rays, the detectors here, and here the patient is going inside the X-rays. And so this is a kind of imaging inside the body. I will come back more in details of all these applications and all these equations. But here just I wanted to show you the main idea. And you want to make either a 3D or 2D, 3D because the whole body you want to see, or just a tomography. Tomo means just a section of the body you want to see as an image. And if you have a section of the body, for example, F here represents the intensity of the material. When you have a bone, it is more absorption, more dense, so more absorption. And here is what you have measured on the detector, because this is the position of the detector, and this is the angles around, for example. And again, here you have to write the relations between F and G. Here, these relations can be written as what is called the Radon transform. I will be back on this more in details on the board. And here again, the inverse problem is from this data, try to find this object. This shows a little more in detail here. This is an application not in medical imaging, but in non-destructive testing applications, NUDT. Here we had a block of metal. Inside of this block of metal, there was a hole. The red color represents the hole inside the metallic object. For each position of X-rays, we obtained a radiography, like the radiography that you do in the hospital. These are the radiographies around the object. And from these radiographies, which are these functions, you want to reconstruct the 3D function F. This is the inverse problem. If you look just, this is the 3D application. If you just look at a section of everything, here you will have just one line, and here you have a section, a 2D. This is a section, and these are the lines. And so the inverse problem here is from these lines, from these measurements, try to find this function. In the title of the talk, we had computer vision. So here is an example of computer vision. This is the example of in tomography that just I showed. We can say that these inverse problems also arise in computer vision. Imagine a situation that you have seen a very nice statue, and you want to have a 3D representation of this statue. One of the ways that you can do is to take a picture here, go around, take another picture, take another picture, take another picture, all around of this. So you have taken a picture here, a picture here, a picture here, a picture here, a picture here. And one of the problems in computer vision is how from these different pictures taken all around of the object make a 3D representation of that statue that you have seen. So this can also be written as an inverse problem. Don't look for no on the equations, just the idea. I told you that in place of X-rays, you can send the microwave on the object. At the other side, you can measure what is called diffracted waves. And from these diffracted waves, you want to characterize, you want to make an image of the body. And here, just to show you how complex can be an inverse problem, I have written here these equations. What I am going to call the object is this function, which is related to the variation of index, some index of the object. In microwave can be the variation of permittivity or conductivity, or the complex mixture of permittivity and conductivity, for example. If it is not a microwave and it is in ultrasound, this represents the variation of index of refraction. Anyway, this is a quantity that you want to try to obtain. And what you measure outside here or around here is what is called the diffracted wave. If you want to write, the first step for studying an inverse problem is to write the equations, to do modeling, to write the equations which relate what you measure to what you want to observe. How to write the relation between what I can measure, which is diffracted wave, and what I would like to know, which is this function. Here you have to write the equations of Maxwell equations, equation of propagation of the waves. And here I simplified everything. I have written it in the form of two equations. The first one is this relation to this through what is called the green functions. For now, just if you do not know, it is not really very important. Just I wanted to show the complexity of the problems in different situations. But in these equations, these are the green functions, and this is the total field inside of the object. So you have diffracted wave that you can measure. You have the unknown object. The relation between the two also depends on some unknowns, another quantity which is unknown, on which we are not interested. But it comes inside the equations. And this unknown function, which is the wave, the wave inside the body, is the incident wave plus again another function with another green function that you have to write. And you see that here the relation between G and F is a more complex relation. And you have also some intermediate quantity which comes in the equations. And unfortunately, this intermediate equation, this intermediate quantity is related in a nonlinear way, in an implicit way, because you have here inside the integral and outside of the integral. But so the problem is a nonlinear problem, absolutely nonlinear problem. But if you do what is called a Born approximation, which assumes that the field inside the body is approximately equal to the incident field, which means that the object is not too much diffracting, is slowly diffracting. If this approximation is true, then phi becomes phi 0. Phi 0 is known, and the relation becomes a linear relation. So through this example, I wanted just to show that how a nonlinear model can be simplified to a linear model, and again, trying to solve this linear problem. Yeah, this is a fourth example that I may show. This is in optical imaging, diffracted optical imaging, not the normal optical imaging. And here, again, you can, in optical imaging, you do, what you can measure is in the Fourier domain, and what you can measure is the absolute value of the Fourier domain, and the relation between the unknown and the observed quantity is a Fourier transform relation. And so in this case, you can see that what you are measuring is not absolutely in the same domain that what you wanted to see. Actually, this is the model of my hand. Here you have air, here you have the soft tissue, and here you have, this represents, this color represents the bones, for example. And so what has measured here does not show any image. But from this, you want to obtain this. This is the quantities who are here, and this is the quantity which is here. And the mathematical relation which relates these two is a Fourier transform. What is the time? We had to make a break. 10 minutes, okay. So let me go a little faster, and then we will be back more in detail. So in this first course, just I wanted to show you very globally what will be the different applications of these inverse problems, just to interest you to follow the next part of the courses. And we will go more in details on the board later. But for this first course, let me just show you that this, the content of this course can be applied in many applications: X-ray tomography, gamma ray computed tomography, microwave tomography, ultrasound tomography, positron emission tomography, magnetic resonance imaging, MRI, photoacoustic imaging. In radio astronomy, when you want to see the sky and what there is in the sky. In geophysical imaging, when you want to see inside the ground, if you are looking for oil, for petrol, one way is to just make a hole and go inside the earth and to see if there is something or not. You cannot do that all the time. You can make a hole here, go down, and try to see what is there. You can make another hole somewhere 2 kilometers farther. And inside one of the holes, you can emit something. At the other side, you can measure the results of the interaction of the emission. And then you can make an image of the section between the two holes. And this will be a good way of looking, for example, what is inside the Earth. Geophysical imaging. I mentioned non-destructive techniques. All the techniques where you want to see inside of an object for testing if it is okay or not okay, if there is a hole inside or if there is not a hole, if there is a crack or if there is not a crack. So non-destructive applications. Just for now, I have talked about an image, and just I showed that the image was a function, a scalar function of the two coordinates of the space. But sometimes you have color images. Actually, a color image is just three images: red, blue, green, RGB. And the mixture of these three images makes a color image. What is called hyperspectral imaging is that not only you may have three colors, you may have a great number of colors. So for each pixel, you have not three values, which are RGB, but you have a spectra. And so it means a spectra of images with different waves. And this is the application of in hyperspectral imaging. I will show you probably some of the examples. And all the areas which is called teledetection or Earth observation or space observation methods. Radar, you may know very well, many of you, about this. Synthetic aperture radar, infrared imaging, and for all which are the surveying and tracking security systems and so on. So I am not going to show all of these applications, just in a few minutes that we have. Again, coming back on the applications, this is CT scan, X-ray tomography. I didn't put the others here. Okay, I summarized a little. And let me just stop here. For the first example that I showed you, we had this relation. Look at this. That was the variation of the temperature. This was the variation of the length. This was the impulse response or the characteristic function of the system. We can call this input, output, and transfer function or impulse response of the function. The relation between the two was a convolution. If you know F, if you know H, computing G is a convolution operation. It is very easy to do, no problem, not difficulty. But if you know G and if you know H, trying to find F is the operation, inverse operation of convolution, which is called deconvolution, and it is more difficult. So the word one deconvolution, and the opposite at the other side is deconvolution. The second example that I show you, this was the object. This was the observed image, or you can say input image, output image. The point spread function. You can see the analogy between these two equations. Both of them are just convolution operation, due to the fact that here you have t minus t prime, sorry. And here you have again the differences here. So this is a 2D convolution. Again, the inverse problem is called deconvolution, or more commonly is called image restoration. In computed tomography, look at the equations. They are very looking here, x and y, they become r and phi. Here you have f. And in place of this function, you have another function, which is more specific. This function is no more, this is a delta function. You find x and y here, and you find r and phi here. you can see that the relation is no more a convolution operation, but is more specific. This is the Radon transform. I will detail it next session. But what is important is that all these equations looks like together. There is something which is common in all of them. And the last example that I show you, which I called it Fourier synthesis, because the relation between what is observed, which was the Fourier data, the unknown, and here you had one expression of the Fourier transform, and so you have this relation. And what we can say is that in general, I can show this, and this in a general form, which is G of S. S can be T, X and Y, R and Phi, U and V, anything. F here. R can be X and Y, X prime and Y prime, which is the same actually, or T prime. And you have here a function, here, and here you have a function which depends on R and S. Here you say T and T prime. Here is X and Y, X prime and Y, X and Y, X prime and Y prime, Y prime. Here you have X and Y and R and Phi, which is inside. And here again, U and V, X and Y here. So this is a function which depends on R and S. And then you have this general equation that we are going to study more in details in the future. So what is called the forward problem is when you know the characteristic of the system. This is called response of the instrument, or characteristic function of the instrument. If you know the characteristic function of the instrument, and if you know the unknown, computing G is the forward problem. There is not any particular difficulty. I will show you that this can be done very easily. But what is more difficult is when you have observed G, you know the instrument, but and this is the inverse problem that we are going to study more in details. Yeah, this again summarizes the last slide for this morning, for this session. I have written the last equation that we saw again in a different form. F unknown, G observation, H the operator which goes from F to G. This is again the equations that I have written here. I added here something which is called the errors. We will talk about this. There is always errors because all these are the mathematical model of some reality. These mathematical models are just a simplification of the reality. There are always the errors of modelization, or errors of the measurement. So the importance of this error is important also to add. If the system was, this is a linear relation that I have written. This is the general relation. H can be linear or nonlinear. Here is the general linear. If this function is dependent also on R minus S, means that R and S are the same representation. This is, for example, in image processing. Then the equation is called convolution, which can be 1D, 2D,